Okay. Okay, so this is ECE 3030. This is a review session for our first midterm. As I said, I'm going to try and upload this to YouTube, my YouTube channel, so those that can't make it. But obviously, having one-on-one rapport is a little more beneficial. You can get all the questions off your mind, off your chest. What I was going to do is, as I also said in class, I'm going to try and go through the 4 PDFs, hitting the hot points, which are probably the more testable items, by the way, and then open it up the floor to questions. Okay, if that's okay, and you can challenge me as I go through as well. Maybe that shortens the question and answer period. Okay. Oops, doing the wrong thing here. Control L. Okay, so I started off with examples just so that, because I think some people are visual learners. I'm a visual learner, and so I kind of wanted to put in your brain the idea of what some of the devices look like. But the devices are going to be in midterm 2 and midterm and the final exam materials, so it's not formally there. But it just gives us a talking points to understand when we talk about these foundational things like velocity saturation underneath the field effect, in the channel, or mobility in the channel, and things like that. You maybe have a context that it's in this transistor configuration. So this is not formally testable, but it just kind of puts that imprint in your mind. And then you can see the blow up, and you can see the channels going to be skirting that interface. We will drill down to that. Go around. We'll drill down to the specifics at a later date. Okay. So. And then I showed you the context of how this is all useful to try and bridge the gap between semiconductor devices and circuits, so forth. And this is DRAM technology, and there's the DRAM trench capacitors, and this is how it starts to look as the hierarchy. So the transistors actually become really a small subset of the whole thing. You see all these highways and byways of metallization. And there you can see a cutaway. It's a little black on black, not as great quality. And here, someone has actually destroyed a wafer by soaking in an acid, and all the dielectrics that separate the metals was etched away, and now you see all the copper. So I think there's at least 2 different textbooks in my field that have used an image like this for their cover art. And so then you can really see in full glory what it looks like. There's another light. I'm going to put on another light here. Okay. Because I might do a little board work here. Okay. So it starts off with materials, properties, crystallography. And so hopefully you started to put the connection together. I wanted you to glean from crystallography this thing about when we get into the origin of bandgap. Because the crystallography matters, because it's going to be the distance between the atoms that really triggers it. If the distance, it's kind of the mama bear, papa bear, baby bear, it's just right, because if it was a little bit larger, it would be metal. If it was a little bit smaller, it would be an insulator. Right? So it's kind of just right and becomes that semiconductor. So you have the materials properties where you can have single crystal, the polycrystal, and amorphous. And clearly now, as we've studied mobility, you can see how these might attenuate the mobility. Single crystal is going to be nice and perfect, so the electrons or holes are going to zip right through. And you can see the polycrystalline is going to be scattering and so forth. So obviously that's less desired. The amorphous is going to be just a pea soup of confusion, and it's not going to know where to go. It also scrambles the bandgap too, because now we don't know where the atoms are relative to each other, so sometimes you kind of even lose the semiconductor properties. And so then I was just trying to tie in the fundamental chemistry and really tie it into, let me blow past some of this, into what I think is more important. So I'm just kind of reminding you of the fundamental chemistry. there's enough testable material that I'm not going to go back and test you on some freshman chemistry thing. Okay, I got enough to challenge you with. But having an understanding that we have the Pauli exclusion principle, you start to stack these in. You've got one electron spin up, one electron spin down, right? That idea that everything has to have a unique quantum number. As I load this up, as I start to fill this in with electrons, we're going to start at the bottom like I'm filling up a gumball machine, and all the little gumballs are going to fall to the bottom, and I'm going to fill up and stack up the levels, right? And so, here's 3p. I'm going to get this, could get up to 6 electrons. Spin up, spin down, spin up, spin down, spin up, spin down, right? So if you have that chemistry foundation in your head, then, then when we, and recognize that the atom has sort of this wave function, this probability of where the electron is. So it senses what's next to it. It's not independent. So if I start to merge this into that crystal, they are going to sense each other. And so, we're going to make, like the classic ones are going to be silicon and gallium arsenide. Those are the two that we tend to fixate on for these foundational classes. And so there's a bonding. This happens to be ionic bonding, so this is your table salt. So there's a Coulombic attraction. They want to come and unite. So remember, gallium arsenide has a little bit of an ionic flavor to it because the one's on the column 3 and the other's the column 5. But the dominant bonding in the materials we care about are covalent. And so they're a sharing of electrons, where this hydrogen has 1 electron in its valence band, and this carbon has 4 in there, and so then they share, and then they satisfy all 8, right? So they're all sharing, they're blending, so shared electrons from the carbon, shared electrons from the hydrogen. So I end up with the 4 covalent bonds. However, I hope you recognize this is wrong. This cartoon is too simple. What's missing from this? Ben?
This is actually a 3D structure.
Yes. What's missing? Key term is going to be the directionality of the bond, right? The directionality of the bond. So as I put this all together, right, before I get to tease about the directionality a little bit more, we have a preferred bond distance, right? So there's this ball and string, the spring and ball concept. So whether you're plotting energy or force, there's all these different variables. It basically comes to the same thing, where there's going to be an attractive force, the Coulombic attraction, the covalent attraction, and it's going to try and bring these atoms together. But as the electron clouds start to interact with each other, that's a short-range repulsion, then this just goes through the roof. So they find a harmonious distance between them, and that will become the distance in our crystal. So this is the preferred, once they form their bond, that'll become the preferred distance. Now recognize it's more like that spring, because I have vibrational thermal energy, because I don't really live at absolute 0 Kelvin, right? Finland may be pretty cold, but it's still got some finite heat to it. So I got some vibrational energy in the atoms. And so here you can see it stretches when it gets hot, right? As you expect. This is going back to the crystallography, so you can see, like, this is a weld, but for semiconductors, this was kind of tying into our liquid crystal display, where if I have bigger grains, I'm probably going to have a better mobility, right? Because I have less scattering. You can see the electrons going through this, it's got more obstacles, whereas here it's going to be able to go through these bigger crystals and have a better performance. Yeah, so here. But you put it all together. Actually, let me come come back to that because I started the discussion on directionality. So here's the preferred bonding. So whether it's again, this is the force or energy. Either way comes, and you end up with the preferred. Here's the bond length in energy space where it's this well, and here's the force. What you're looking for is the force is net zero, the force of repulsion and the force of attractive balance, and so it ends up being exactly the same. So it's either way you want to look at it, but they end up being. Really want to do is remind that they are directional. This is important. Covalent bonds are directional. So we get that sp3 hybridization for most of these semiconductors, where the s orbital, which has a spherical flavor, and the p's have this dumbbell shape. But this is py. Remember, how many electrons do we put in the p orbitals? 6, right? So we have 2 in the x, 2 in the y, 2 in the z. So we got 3 of these dumbbells, right? And so then those 3 dumbbells get together with the 1s, and they merge and they become sp3 hybridized, where we get the 4 electron clouds that protrude. So here's my 4 electron clouds protruding. And what's the angle between those? 109.5, right? And it's simply a Coulombic repulsion, right? Because this electron cloud does not want to interact with this electron cloud, nor does it want to interact with that electron cloud. So they find harmonious. They're bent as far as they can from each other. And if they bend a little, if this guy wants to get away from here and bend a little bit more and go to 107. Then now he's closer to here, and this guy says, you ain't coming over here, and pushes him back. And so there's this yin-yang, and so 109.5 is the way you can space 4 bonds out of the 2 pi steradians of the whole complete solid angle of a single atom. So that now sets in motion that I have this bonding, I have this interatomic spacing that is set, I have a directionality to it. So as I start to parse this together into the semiconductor, I'm going to have certain interatomic spacings going in this direction, certain interatomic spacings about going in this direction, certain interatomic spacings going in that direction, and I'm going to have a unique solution in all these different crystallographic directions. Remember, we're going to that band structure concept where k is a momentum vector. And so that's going to be going through 3D-dimensional space, which is going to be influenced by the periodicity of the atoms. That's going to be very, very important. That's tying into the foundation of where the origin of bandgap comes from. Okay. So that's the more key underlying storyline that I want you to get. That's certainly going to be represented on the test. Let me go back in the slides and clean up a few things that I just wanted to point out that I skipped over, because I wanted to keep pushing that central theme. Okay, so we got the grain boundaries. We talked about that. Recognize there's also, just want to kind of point out that there's ways that we can look at this crystallography. I think this is kind of showing one. It comes up a little bit later, but we can inspect it through microscopes, X-ray diffraction. You'll see later. And so when we make these observations that I have a crystalline, amorphous, or polycrystalline, recognize I have diagnostic tools at my disposal that could reveal these. That I can actually measure them. Right. So just kind of understand some of those techniques, be able to describe them in a simple term. So here you can see structure-property relationships is something I like to also beat home on. So here is the different. This is a crystal. This has got one kind of polycrystalline behavior. This is another, and they manifest. They're completely different. Their opacities are different. How they operate, this could actually perhaps operate as a filter, water filter perhaps, where maybe because it's got this high porosity, maybe water can go through there and trap some impurities. So depending upon the crystallography, I get a different outcome. So structure property. This is the one example I was trying to point out to you that's really highly germane to semiconductors because it's in everything most of the things you have. Of course, iPhone didn't go to OLED displays yet. They're still in the active. I guess I'm blocking your view. They're still in the active matrix liquid crystal display mode for their cell phones. So this is what my my computer monitor is, right? The white light and the polarizer, and then a liquid crystal medium, and then the analyzer, and then my eyeball for viewing. And so the key is when you focus in on this, so I got this pixelated screen that this maps onto, each pixel has to be driven by a transistor. And so that transistor is perhaps silicon that is deposited onto my amorphous glass. So when it is amorphous silicon, I have, due to the amorphous properties, its mobility is very low. Right? It's all that scattering, right? It's just kind of confused. It's just an obstacle course for an electron to go through it. If I can give it some heat treatment, zap it with a laser and allow it to melt and then recrystallize, then maybe it can recondense like that welding arc that you saw, and maybe it starts to make little grain boundaries. So then my mobility goes up, and I can make my transistor smaller and still have enough current drive to drive the whole pixel, right? So because that's a higher mobility, I can make the transistor smaller. So there's a structure property relationship. Better crystallinity, higher mobility, which equates to a higher higher brightness liquid crystal display. Yeah, here it is. It's called a thin film transistor, TFT. That's driving this. So it's a little guy there off to the side. Talked about that. I'm not one to sort of be challenging you with kind of dumb definitions too much. We have all these different crystal systems, and I'm not. I try and make you memorize the foundational, the fundamental principles, not all this kind of ancillary stuff. So yes, there's 7 crystal systems. Yes, there's 14 crystal lattices. But I'm not going to be the one that's going to sort of say name them all or all this kind of stuff. I want you to understand how this equates to a silicon semiconductor, wafer chip. So start off with the crystallography. We do have to delve into it a little bit because it becomes the ingredients of the framework of that semiconductor. So we have simple cubic, body-centered cubic, face-centered cubic. You will not be asked on the exam in a 55-minute limited duration examination to calculate the packing factor. That is not right. If I haven't made that clear, it's going to be foundational word answer questions. And that's what the homework complements, is the quantitative, where you got a whole week to challenge the TA. Hopefully you guys challenge the TA, ask them your questions and so forth, and do the quantitative, where you have to have a whole week to sort that out and find your divide by 2 error and things like that. So you're not going to be doing that, but understand that these are the frameworks of that. Yeah, so this kind of atomic packing factor and so forth. And theoretical density and stuff. So, understand it. I'm not going to say draw a 111 point or so forth. Those are not the kind of questions I go after. The crystallographic directions and so forth. I think you should know that because it relates to when I want to make a device. It relates to whether I process my wafer right side up or upside down, perhaps even. And so we got all those crystallographic directions. But I do hope you understand at least the difference between a point, a line, a plane, right? I'm going to have, I have a 1, 0, 0 plane, and here's the 0, 0, 1, so I'm going to have a certain plane, and I'm going to have a certain density on that, and maybe when I go to the 1, 1, 0, I'm slicing through the material at a different angle, and therefore I'm going to see different atoms on there, different spacings, and so forth. And here it's at the 1, 1, 1 coming in at an oblique. That tends to be a high density plane. Yeah, here's some of those. So I think we get back to our main story of directionality. And so then this is kind of the workhorse for us. This is our silicon, this is our gallium arsenide. And if you really parse this together, and again, I'm not going to have you draw this, but what is it composed of? It's two face-centered cubic lattices interspersed. Because if you do your accounting, some math accounting, you realize that I've got 8 vertices, 2, 4, 6, 8. I should have 6 faces. 1, 2, 3, 4, 5, 6. And I've got a few extra atoms sitting around. This is an extrapolation of that. This is an extrapolation of that. This is an extrapolation of that. And I guess that's an extrapolation of that. Right, so I got 4 extras because I have 2 FCCs interspersed by a quarter A in there. Right. This is a quarter A in the X, quarter A in the Y, quarter A in the Z. So now this becomes the framework when I put my electrons into my valence band configuration. Recognize these are all crowding into each other, right? They're influencing each other. This is a quantum mechanical distance. It's short enough that they're quantum mechanically sensing each other's presence. And that's the key. And you should recognize that depending upon how I travel, how the Starship Enterprises travels through through that void, I'm going to be hitting different planets, different atoms, and different periodicities, right? So it matters if I'm an electron going through there, in which direction. I'm going to see a different periodicity. Here's maybe a little easier representation, because when you go over to gallium arsenide, which we magically, just to confuse you, this is diamond, and this is zinc blend, and all it's doing is just telling you that those extra 4 are the other sublattice. So if these are gallium, that's arsenic. Or if that's gallium, then this is arsenic. It doesn't really matter. It depends just how you where you want to put your origin, your 0 point. But now, because of the crystallography, I can imprint my wafers with these kind of features, so I can determine which is which, so I don't process the wrong wafer in my clean room. And if it is crystallographically perfect, it's diamond-like, and so I can cleave it or do whatever, and I can express those different facets. So it turns out the 1, 0, 0 plane is very low density, so it's easily attacked by an acid or a base, and the 1, 1 on plane has the higher density. So if I immerse this in an acid with this mask up here, this etches down and it actually self-limits into this pinch. And this one will come down, and if I probably left this in the acid for another 5 or 10 minutes, this would also come down and self-limit. So people will do this where they'll put an optical fiber in there and do micro machining, so I can do some photonics where I'm putting an optical fiber with another optical fiber perhaps. This is maybe waveguides. I can shine light through there if it's designed properly. So I can micro machine it. Yes, Ben?
You take the mask off when you use it?
It depends. Usually the mask is a sacrificial layer, but it depends. Sometimes it might be incorporated. We've done both in our process flows over the years. So because of the crystallographic, you can be like a diamond De Beers. I can go in and I can cleave that along the crystallographic facets, just like I'm cleaving a diamond. And I've done this. This is it's actually fairly simple. It's tedious, but it's simple to do. And you cleave, and you'd actually, if you get two perfectly cleaved facets, then they end up being quite reflective, and you end up with this Fabry-Perot cavity, which it seemed like people had not really seen that in prior classes. Fabry-Perot in physics. Well, it's basically, how many of you are musicians? None of you? One of you. Okay. Well, it's just like plucking a guitar string or a violin, right? I have, or taking a jump rope and tying it to two brick walls, right? And so I have a foundational frequency, and I have a first harmonic, and so forth. Well, the same thing goes that I can count an integer number of wavelengths of light that go through that cavity. And so if I have two reflective mirrors, this forms a Fabry-Perot etalon and forms the laser diode. But it's formed by the fact that I had perfect crystallography. And so if I cleave along the facets, I get a nice cleaved edge. If I cleave at the wrong angle, I'm going to get a ratty edge that is going to be a dead laser. So you get fired from De Beers if you don't cleave along the right crystallographic planes. You get fired pretty quickly. So here's some of my old cleaving, some waveguides. I was just trying to throw that in for some eye candy. And then if you remember, so this is not testable. I'm deviating. Let me keep on task here for the test. Yeah, here's the Fabry-Perot. So ways to inspect. I kind of touched upon this earlier, but I understand there's a structure-property relationship, so I can go in and test some of these structures to tease out what the properties may be. So I can interrogate it with X-rays. Why do I need X-rays? Why don't I throw radio waves at the semiconductor?
You need a really small wavelength.
Yes, but why?
Because bandgap.
No. Very good, but it's wrong in this context. Yes. Sweet. Okay, I love it.
It needs to be on the scale of the lattice spacing.
Yes, it has to be commensurate. It's like you're a blind person and you're inspecting. You need to have something that's feature size that you can feel. You're not going to feel micron size gap in this table or so forth. But something that is commensurate to my thumb, I might feel that imprint. And so the X-ray is of a short enough wavelength that it's comparable to the interatomic spacing. So it can see it, it can bounce off it and sense it. Too big and it's not going to miss it, too small and it's going to also miss it, right? Do you remember there was some movie where they shrank everybody in a submarine and put them into this diplomat's body, and he was, and they're trying to do an internal repair. Do you remember that movie? It's an old, like 70s movie. What was that? Huh? Anybody? So you need to be the right size, right? Or you're too big, you're too small, you're not going to be able to see it. Okay. So here's just going back to simple diffraction theory. And so you have a plane wave coming in. So this is kind of the ingredients of how that X-ray diffraction works. Right. So I have a slit, and that light comes in, and it's going to be expressed into this periodicity, this periodic display. So I'm going to have bright spots and dark spots and bright spots and dark spots. Right. And so I get this. It's actually a sine x over x squared, and you get this as a sinc coefficient. And so then this manifests as one. This is indicating I have high intensity right here, and then side lobes that are more moderate intensities, and they attenuate as they go off. Yeah, exactly like this. That's what it looks like. Bright. So here it's saturating the camera. It's so bright, it's saturating the sensitivity of the camera, and so this bleaches out. but you can see all the different. And so remember, we could actually even do real-time image processing here. And what happens if I take off that fundamental? Anybody paying attention in the lecture that day? I'll take the fundamental off. Actually, it's the next slide, I think. Yeah. If I take this fundamental off on this letter E, what do I get?
Outline.
You get the outline, exactly, right? Because it's just an expression of, that's the fundamental that colors it in with the DC color component. And then the outer are the higher frequencies, which are representing the edge pieces, right? And so if I block that, right? So this is what? In this image plane, I get the Fourier transform, right? And if you take the Fourier transform of a Fourier transform, I get the real image back, right? So this is the image plane. So with that kind of way, I could actually inspect the semiconductors. That's how we do it. We make semiconductors that would be. We take that transistor, for instance, and we might. Risk going all the way back to the beginning. But, maybe how did I get this picture? Well, I probably took that wafer and I sliced it open. So I destroyed the transistor, destroyed the circuit. I sliced it open and then I made it, and then I etched it to the point that it's electrically thin. What you actually do is you start off with a disk and then you etch a crater. And eventually this pokes through, so this ends up being a hole in it. I'll punch a hole in this. And so right here, this becomes so thin, it's electron transparent. So if I send my electron beam through this very transparent, and the transistor's sitting right there. Okay, you got to kind of know what you're doing, so you got to put the transistor right there. I send my electron beam through there. I am going to get a Fourier transform of that, and then below that, I'm going to get in my electron column, my electron microscope, I'm going to get another image plane where I can actually see that transistor. So if that didn't make sense to you before, hopefully it does now. So the diffraction pattern, which will tell me the crystallography of the specimen I'm inspecting, and then the image plane where I actually see the transistor, the device, the solar cell, the photodiode, the LED, whatever. And so if I'm sending, just like I'm sending light through a slit, which as you saw before, it's that sine x over x kind of thing, was the Fourier transform. If I do the diffraction through amorphous, it's going to be completely scrambled because the diffraction is going to be completely random. So I'm just going to get a blur. And the other extreme is the perfectly silicon. I get all these nice dots where I might have the center be brightest and then the higher frequencies be a little dimmer. And then the polysilicon, why is it concentric circles? Because one crystal is oriented like that, the other crystal is oriented like that, the next crystal is oriented like that, and so on and so on and so on. So if my beam is 2 millimeters, then I'm going to integrate every one of those little crystals, crystallites. And so it's basically taking this and spinning it around. Right? So if I take this single diffraction pattern, spin it, all these dots turn into circles. There's that game you do as a kid where you put the pencil in and you make those swirly things. What's the name of that?
Spirograph.
Spirograph, yeah. So I'm just doing spirograph with my silicon crystal. And so again, you know, what I challenged you before, I have to have a wavelength or something of commensurate size. So here's the X-rays that are of a wavelength that's equivalent to or similar to the interatomic spacing. So I end up with this extra wavelength, path length that these are transmitting, and then it goes out. So I can inspect the crystallography by a multitude of ways. Yeah, here's just another example. And yeah, and here you can see someone came in and laser blasted this, so this is like a damaged crater of whatever crystal of silicon it is. And so here in the center of the blast, what is it? It's like one of those, what's the Chinese space station's going to come down to Earth? So it came down and blasted. Supposed to come down, what, next year? So this has come down, and here it's getting to the edge, so it's starting to get a little bit of crystalline. Here's a little bit more, and this has now been uncontaminated by the blast. So this is fine. Okay. So recognize, so we've got this perfect crystal, but nothing's perfect, right? Except the Rutgers game, right? So, so we got point defects, we got line defects, we got planar defects, right? So we can have a substitutional, but recognize we're going to want that later, right? Because that's going to be our doping. I can have an interstitial. That's probably bad, but maybe this guy is just lost and he's trying to find one of these vacancies, and so this guy just hasn't found his home yet. So this is kind of maybe an intermediary stage, but it's probably going to create some problems there. So that's substitutional, interstitial, vacancy, and this is a Frankel defect where it's popped out of place. It's like I popped my shoulder out of place again. I used to do lots of volleyball and I can't play anymore. This is popped out of place and you just pop it back into place, right? You just give it a little temperature or time. Yes, yes. Ahmed.
So the type of doping that we do later on is mostly substitution.
It is only substitutional. If it's not going in substitutionally, it's not electrically activated.
But how do you control that? I mean, we only...
Mother Nature wants to do that, right? Because satisfying the 4 covalent bonds, that's what it wants to do, right? My Hope diamond wants to form a perfect crystal if I give it enough temperature, enough time. So if I introduce the dopants in a way where I give it enough temperature and time, it will pop in as this replacement impurity. It's going to replace the silicon atom. Yeah.
Doesn't that mean that B and D would be unstable then, since they don't have that bonding keeping them there?
Yes, they are unstable. Yes. So this is the plague of our semiconductors. So usually our crystals are never perfect. We always have some defects laying around. The question is, are we keeping that to a minimum that it's tolerable? Yeah. Yeah, in fact, defects are sometimes used. That's your flash memory, right? Your USB sticks and all that. And here they just loaded this oxide, this gate oxide up. And since I've already tried to give you the idea of what a transistor looks like, you can maybe start to realize if I put little crystallites in there, that becomes areas that I can put charge. And so later we'll see how the threshold voltage of a transistor works. I haven't taught you that yet. But this will shift that threshold voltage, so I can essentially program this. I can turn this transistor so it will represent a 1 or a 0. And so I gotta have millions and billions of these to represent my latest cat video on my USB stick, right? Yeah, so this is the same thing. So here's a line defect. Something went wrong. I was growing this and it propagated up. I ended up getting an extra layer, and so that's going to propagate up. And so that means all these atoms into the board are unhappy, right? They're unstable. They have one missing covalent bond. So anything that comes near there, an oxygen atom or something like that, may very well be absorbed and lead to there's going to be charge associated with it because it's not balanced. It's very unhappy, so it can be really a problem. And these can actually even move, kind of like San Andreas fault. These little defects can sort of move through the crystal over time. Here's some others. There's all kinds of different ways that you can make these incorrectly. Screw dislocation, where it just kind of, we don't have to get into the fine details of them, but you can see. Okay, going back to this, to being able to inspect, here's one where it's different polycrystalline material, and maybe I stain etched this, so I applied a mild acid, which means all those little grain boundaries. It's kind of like, it's like trying to take the grout out of my shower, right? Shower tile. It's like I've pulled out all the grout lines and I see all the tile in full glory. I look at it in an optical microscope and I'm going to see those little crevasses, right? So I can express that. But I've damaged. This is a way to do, so it's a destructive test after I've made my device and everything. I'm finished with it. Maybe I want to test what it looks like. Oops. Misfit dislocation. We want to essentially put anything on anything for maximum flexibility of engineering. Say blue-green LEDs to lasers, gallium nitride. They typically use sapphire substrates, aluminum oxide. But sapphire has low thermal conductivity, so the device gets hot with large current. So we have a critical thickness associated with limitation of what we can put on everything. Critical thickness is the thickness at which it becomes energetically favorable to create a misfit dislocation or skip a bond, a row of bonds. So it's basically the Jenga model. I've created some instability, and the taller it gets, the more energy it gets. So if I want to put, actually indium nitride belongs down here. Let me pick on over here. If I want to put gallium arsenide on aluminum arsenide, they're pretty much vertical, so I don't have that lattice matching constraint. But if I want to put indium gallium arsenide on indium phosphide, I probably should be right around here, and that's what I used to do at my PhD, one of the things. And you put indium of 53% and gallium of 47% arsenic right there, and you'll be lattice matched on the indium phosphide. So you're right there. You go this way, it's indium rich. There's a limit to how thick you can grow it. If it's gallium rich, it's a limit to how far you can grow it. Here's your LED market here. And so there's a limit to how much indium you can put on, because these are now huge. This is even amplified to what the silicon germanium world is. And so you can usually only deviate a little bit about that. We just came out with a paper, actually, where we were doing these two. And it's severe. I mean, we were limited to like 2 or 3 nanometers of this on this to keep it within constraints. And so this is the misfit dislocation. This is basically the Jenga tower. If I grow silicon on silicon, everything's happy. It's all registered. If I have this larger blocks on this smaller, so it's Tetris, but they don't fit, but I somehow forced it, then they're going to distort. And when I distort, those bonds are bending. So those 109.5 degrees are now unhappy because the whole thing has had to distort, like a gummy eraser. Like you have one of those gummy erasers, which you might want to bring to the exam. And so as you squeeze it, it gets longer, right? There's a relationship between squeezing in the X and how it goes in the other direction. And eventually this becomes like a Jenga tower, and it's too unstable. And eventually it's going to skip a beat. And so it's going to make that misfit dislocation. So there's a limit. So this has grown too thick, and it caused that dislocation. This is still within the allowable constraint. So this is still conforming. Okay, so same thing there. So under thermodynamic equilibrium, the upper layer should maintain that lattice constant of the substrate while it builds up the strain energy as it gets taller. The strain energy is high enough, it becomes energetically favorable to boom, misfit dislocation and release. So when misfits are produced, a spontaneous change occurs in the surface lattice constant. And you don't have to know my PhD. I know my PhD, but it's you end up with. Oops, I didn't realize I was going to have to go that far. You end up with this. This is one of my pages out of my PhD. You actually measure that surface lattice constant. So this is the critical thickness. That's from theory. That's what it tells you. And I actually saw that through electron diffraction. I could actually see this pop. And I could freeze it in because temperature and time. If I made it cold, I slowed down the motion of the atoms and it delayed this. Now if I heat treated it later, it would pop into place. They're just waiting for that energy. Yeah. So here's the critical thicknesses. So here's that indium gallium arsenide and gallium arsenide. This is one that is used for 980 pump lasers. I'll give you that story later, but actually my first PhD student formed a laser diode company doing that. Indium gallium arsenide right here. And so there's a limit. So he had to make his quantum well laser diodes within probably about 200 angstroms. 20 nanometers was probably a limit of his quantum well laser. Here's germanium silicon, what Intel is starting to do at the 45 nanometer node. So earlier than that. So this shows you the limitation of what you can do there. This is where, yeah, same thing. These are just different theories. You don't have to know that. You don't have to know that. And this is that diffraction I can inspect. So when I accelerated the electron at 10,000 electron volts, it had a de Broglie wavelength that was equal to the interatomic spacing. So that's how I saw. So here's the diffraction patterns off the surface. And yeah. So then oscillation. This is window dressing. This is not testable. Yeah, let's skip past that. Yeah, but it's being able to put anything on anything. That's the key. And yeah, here's what. 90 nanometer. I misquoted. It's 45 here, but it's the 90 nanometer node was where that was introduced. This silicon germanium by Intel. So here's the misfit dislocations. When they do relax, this is how it manifests. This is a top view, it looks like Manhattan. And from a side view, we see the cracks propagating through. Understand where this all comes from. So we all have to put this on substrates. So we start off with bulk epitaxy, which is a way to make the substrates. Czochralski is a classic one. You're pulling those boules out of this molten silicon. You start off with the little seed crystal, and you pull that out. Pull it out like that, and there it is. Pull it out. So Czochralski's one way to make my ingot. And then what do I do next? I'm going to slice it, take that ingot, and I'm going to slice it into wafers, polish them, and send them into my factory, my clean room. There they are. Of course, this is back when we had people in our factories. And I don't know why this guy doesn't have a clean room. He's probably doing repair on this. And this is probably a university lab where they don't care. Yeah, so this shows the flow. You take the boule, you cut off the ends, maybe you recycle them. You do the wire sawing, and then you do the polishing. Laser, each wafer in an Intel process is going to have a serial number on there, so you know where its whole process flow. You polish it and everything, and you end up with the wafer cassette. And then these are flying around in those little modules you saw in the clean room. Looks like the Star Wars capital city. There's float zone, where you're just combing it, heating it back and forth, and the more passes, the more crystalline perfect it's going to be. So this is tying into the growing a sugar crystal, a rock salt or whatever. You're going through a phase diagram for, this is particularly gallium arsenide, and so you would heat this up with a small amount of arsenic, and the gallium would be the solvent. So gallium would be the solvent like water, and the arsenic would be like the solute, like sugar or table salt. And I would put just a little bit of sugar into my water to make my sugar crystal, right? So I'm going to put a little bit of arsenic into my gallium. I'm going to heat that up, and then I'm going to cool it down. And if I do everything right, some of it will condense into stoichiometric. There's going to be a tie line. It's going to be tethered to this, because let's use salt, because everybody knows salt. Salt will condense out with NaCl in a stoichiometric relationship where there's 1 for 1, right? You know that. So if you understand that, this is also going to precipitate out as gallium arsenide 1 to 1. Because just that, fortunately, Mother Nature just makes everything go to order, right? It wants to. That is the lower energy configuration. Horizontal bridgman, not really used because it picks up contamination from the crucible. So this is less important. And so, getting back to the semiconductors, right, we have the metals, we have the insulators, and the semiconductors. And why is this a bar and not a point?
Adjustable range.
Yes, because now you know we can adjust the range through our process engineering, through my doping and all that, which I can choose, right? I can design that, I can process that, and I can hit that with fairly high precision. So these are processing techniques to modify the substrates. I can do implantation, I can do diffusion. Here's the ion implanter. Actually, in Caldwell, we used to have an ion implanter. I had to actually mothball this to make room for my lab. Universities don't often, it's too much of a headache, keep these. If you need them, you usually just buy it as a rentable service. So it's basically like billiards, right? You're just coming in with different atoms, and they're hitting the crystal, and they're coming into that crystal. And if they hit something, they're going to dislodge it, right? That Frankel defect we saw earlier. So the crystal may look like this at certain axes. You may find some tunnels, so it's like you're Luke Skywalker going down the channel, and you're trying to, And so, depending upon the crystallography and the incident of the ions, you can marry up the angles if you know the crystallography, and you get different effects. High energy ions going to come in, and it's going to create this whole collateral damage, where it's just going to continue to ricochet on down the line and cause all kinds of damage. And that's a light ion. It's going to come down and plant itself very deeply. A heavy one's going to come in and create a lot of surface damage, but not go very deeply. But we can do the modifying the doping, right? This is one way. It's kind of a crude way. There we did 4 different implantations, creating 4 different doping profiles. Now we are going to get back to this. This is a slide foreshadowing of the transistor, where we will do ion implantation and finish up our planar transistor. That was a real workhorse in the transistor technology. So we could put that implantation precisely at the SiO2 silicon interface. We can do photoresist, photolithography. We can define, we can basically pattern etch. Let me skip past that. So then ways to make wafers. We're depositing, we're doing epitaxy. What does epitaxy mean? It's a good test question, epitaxy.
I always thought it was just making layers.
No, that's deposition. Deposition is just putting some atoms on the surface, and they just sort of, Epitaxy means they're going to come down and they're going to move around, and they're going to find their happy point, and so they're going to condense, and they're going to, so if I start off with a crystal, it's going to continue to grow in registry with the crystal below it. That was the earlier things, the misfit dislocations and all that. If I cooled it down to a low temperature, I'd just be depositing amorphous goo, right? It'd be a Wagner power painter. It'd be spray painting these sick colored walls here. What color is this? Okay. And so it's just spraying paint, and so whenever the paint sticks, it's going to dry, right? But that's not what I want. Epitaxy means it's going to move around in a correlated manner, and it's going to try and break some bonds, reform some bonds, break some bonds until it's happy, until it's condensing and propagating that crystal.
So it's growing with the same crystallinity?
Yes, yes. Yeah, that was the, yes, because that's what this was. That's what this is. So I started off with that bulk substrate, and I go into one of those epitaxial reactors, and I'm depositing gallium arsenide on gallium arsenide. And here, I'm depositing indium gallium arsenide on gallium arsenide, larger lattice constant, so it will squeeze and conform to form up to a point until it says no more. Yeah, this is the epitaxy, this is the bulk substrate. That's what it's trying to represent. So I can do I can make rock candy, I can make rock salt through phase diagrams and so forth, but it's not a way to mass produce. This fell out of favor. This liquid phase epitaxy, where you start off with a liquid. This is basically how you make rock salt, rock candy. You start off with a liquid, and then the liquid comes in contact with the substrate. So you slide this underneath and they come into contact, and as you slowly cool it, it condenses. That's liquid phase epitaxy. We used to do that in my lab, but then we stopped. CVD, this is a little more manufacturing style. Here's CVD. Here's CVD. So you're just, instead of starting with a liquid, you're starting with a gas. You have a chemical vapor. And these chemicals come down and they react. And they trimethyl aluminum deposits aluminum. Trimethyl gallium deposits gallium. Silane deposits silicon. So they come down and they react. Here's a more elaborate one. So it's got gallium, aluminum, zinc as a dopant, arsenic up here. So this is a reactor growing gallium arsenide, aluminum gallium arsenide. And it looks like that's the p-type dopant, and that's probably the n-type dopant. So I can make p-n junction gas-al-gas structures with that reactor. So here you see, it's just a plumbing nightmare. This is an MOCVD. We have one of these on West Campus, in Kinnear Road, the Nanotech West. Here's a molecular beam epitaxy. If I really want to get high precision, this is how most of my research samples are produced. We have fusion cells and they deposit, and we can deposit with atomic layer precision on this. And you saw already the reflection, the electron diffraction off the surface, so I can actually monitor that atomic precision. And here you can see quantum well structure with atomic precision. That's a piece of cake these days. Yeah, that's what one of these guys, it's a big just chunk of stainless steel. Okay, that's one. Wow. Okay, this one is less important because this is going to be fodder for your for a take-home problem, perhaps. So I was introducing you to oxidation processes, dry versus wet, where the dry goes into the gate oxide, the wet perhaps goes into the in-between to isolate. Right, so it's just like rust. When you add water, it oxidizes at a faster rate, so you see it balloon up. And so this is the thin gate oxide of high quality, so we grow this in a dry ambient. Yeah, so there's the same thing. put it in the reactors, we grow it. But this is not really, I think this is really the take-home kind of stuff. So there's all these curves and how to calculate. Maybe the only thing to take away, because this is going to be a setup of the FETs, is recognize that the original surface gets buried, and as we oxidize, we're oxidizing from the outside in, and this will become perhaps in some field effect transistors, this will become that channel. And therefore, I'm leveraging a nice pristine silicon interface here that has never been exposed to ambient. So this is virgin silicon down here where this oxide has penetrated down. And so this is a high quality way to make this. The fact that this is oxidized from the outside in. That's the important takeaway point for this exam. Let's skip that. Doesn't matter, doesn't matter, doesn't matter, doesn't matter, doesn't matter. Quantum mechanics matters. Okay. Particle in a box. I think you've had this with physics. I get mixed answers when I ask this question. But again, it's like if it goes up to infinity, I end up with the fundamental frequency, first harmonic, second harmonic, right? I'm going to have, it's basically like the Fabry-Perot etalon, right, of the laser cavity. I have certain harmonics that are satisfied by the boundary conditions. For Fabry-Perot etalon, which is a fancy term, it's just where I have a mirror and a mirror. Here I have a potential energy and a potential energy. Well, what is a mirror to a light wave? It's a barrier. And so here's an energy barrier for this electron bouncing around. It's really the same thing. And so, but recognize, at the quantum mechanical, when you shrink things down, I can tunnel through a barrier. So classical mechanics would say my energy is coming in below this potential energy, and I can't tunnel through Mount Everest, right? Mount Everest is too high. I'm going to have to go around it, right? But at quantum mechanics, I have a little thin barrier of 2 nanometers. I can quantum mechanically tunnel through that. So here you can see it's got, because electrons have that wave-particle duality going on, so I have the wave penetrates. As long as that wave doesn't extinguish by the time it gets to the other side, I have a finite amount, it's non-zero, then I can actually continue oscillating on the other side. And you can see things like that. So then the most important critical thing of this exam is the origin of the forbidden bandgap, which leads to the semiconductor lane between a conductor and an insulator. This is, you can guarantee there's going to be one question on this in the exam. You start off with your single atoms with their orbitals, right, which I load up with my electrons. It's like putting gumballs into my gumball machine. But because I have that crystal, the atoms are close together. They sense each other, right? That there's a magic distance there. And so the wave function associated with this sees the wave function associated with that. And Pauli exclusion principle says they cannot, say, occupy the same atomic quantum number. So they split. One goes positive, one goes negative. It's like 2 plate tectonics shifting underneath each other. One occupies one space and the other goes under, and so forth. And so it's the splitting of the energy levels driven by the Pauli exclusion principle. But this is just 2 atoms. I have a crystal. I have something like Avogadro's number of silicon in a cube of silicon, right? Technically I got, what is it, something like 5 times 10 to the 22 or something like that. I can't remember the number. But it's almost Avogadro's number in a cube. And so that means there's a lot of splitting. So this is the graph I like from Streetman that shows the discrete. This is that Gedanken experiment. I have a bag of a mole of silicon and a big bag out in outer space. And every silicon atom is expressed as individual silicon atoms because they're far apart. It's basically a gas. I squeeze this bag and it liquefies and eventually condenses into my crystal. And now the interatomic spacing is such that the splitting of the energy levels have manifested that the two n states in the 2s and the 6n states in the 2p have merged and blended, and 4 of those have come down here, and 4 of these come out, because 2 plus 6 makes 8, 4 plus 4 also makes 8, so I have a conservation of energy levels. And in silicon or diamond or whatever, I have 4 valence electrons. So I got 4 gumballs to put into this, 4 electrons. And so when I fill up the valence band, I run out of carriers. Yes?
So you said that for silicon, the sp3 hybridization happens. Is that this valence band?
That determines the interatomic spacing. And so that's key. See, if this spacing was nudged a little bit here, a little bit there, see how my band gap shifts so dramatically? That's my key point. It's the lattice spacing, the crystallography, that's determining that band gap, which is why here, if I have different lattice spacing, I have different band gaps. That's why these all fall more or less on a line. Of course, Mother Nature scatters things a little bit, but more or less, the smallest lattice constant leads to the largest band gap because there's the most interaction. These guys, and so these have wide band gaps and are very hard, diamond-like. These are extremely soft and brittle because the atoms are farther apart, so there's less interaction, so they have a very modest band gap. And then depending upon what color I want, I can dial in whatever wavelength I want. Okay? So I can hit Roy G. Biv, I can make any LED color I want. Okay. So the band structure, which is energy versus momentum, which is a vector, is that concept. This is in one dimension now. I have the atoms lined up, they all interact, I get a splitting, and I create the valence band and the conduction band. It's like I'm trying to do an expansion of sines and cosines to represent this rectangle function. And so the allowed functions given by the boundary conditions. So any sine or cosine that is asynchronous with this will not be expressed. Will be a disallowed energy state, right? So if I had something that came like this and went like that, right, it's not really going to propagate in my crystal. It's not going to be allowed. So these are different frequencies that are allowed. This kind of ties back into the letter E image processing that we were doing too. You can see the higher frequencies that are trying to pick up that edge. And so what was normally 1/2 mv squared in my nice parabola of a free particle, right? Because this is energy, and this is k, this is momentum, which is basically p. One half mv squared equals p squared over 2m. So then this becomes k squared over 2m star, where now k is a momentum but also with a vector, so it's directionally dependent through the crystal lattice, and m is now all of a sudden our effective mass that is sensing the crystal. And so certain directions and phases and energies are allowed and some of them are disallowed, so it fractionates into these bands. The free particle doesn't have that boundary condition, so it's free. And then I do the origami and I fold out all space so I can put it on a textbook so I can test you on it. And so here we see. So then, yeah, we just basically do origami. We fold all three-dimensional space. So we do our origami thing. And remember, particle size determines band gap, determines all these things. So So here you can see, just by changing particle sizes, I changed the wavelengths that which they absorbed, the colors and so forth. So quantum confinement is important. Effective mass came from this effective mass. We have probably conduction band, EC, valence band, EV. It might not be shown by the camera. And so this curvature will become the effective mass of the electron. This curvature will be the effective mass of the hole. That curvature. So so the concept mathematically, electron holes can be treated as classical particles as long as the carrier effective mass replaces the particle mass. That's really important property. So we'll use these, which are a manifestation. I think it's the next slide. Yeah. So they're a manifestation of the inverse curvature. So you find that curvature, and it's a reciprocal of that. So the less curved it is, the heavier it is. The more narrow it is, the lighter it is. And now I can do, what's the important thing now? Now I've inserted M star for M. So now I can
use Newtonian physics.
Bingo. Newtonian physics, right? I can use just simple F equals ma. So now I can calculate force, acceleration. Remember my example of avalanche multiplication, right? When you want to ionize your little kid brother, right? So I'm gonna the mass at which I need to deliver that kinetic energy will be determined by the curvature of the bands. So some semiconductors manifest as direct, and some indirect. Silicon and germanium tend to be here. Gallium arsenide, gallium nitride, and phosphide tend to be here. So silicon and germanium do make good electronic devices, but they make very poor photonic devices. So this is what is used for LEDs. Now silicon can absorb light, it just can't really emit light. So we have silicon solar cells. So if you did a more formal solution of Schrodinger's wave equation through all those crystals, all those atoms, all those, you start to get the band structure that looks like this. So this is energy versus momentum. Now you see the different vectors, the 1, 0, 0, the 1, 1, 1, and now you see these different planes. Here you can see the heavy holes, and here you can see the light electrons. These are a little bit more equal. Here's another. So you can even see if there's a heavy hole and a light hole band expressed. And so you can see all of them. Okay. So here you can see. So this determines when this particular material went indirect. Let's see. So now we have that. In class I always said it's like we created our parking garage. We created this parking structure, and now we have this forbidden band gap. So maybe floors 2, 3, 4, 5, 6 are empty, are forbidden, and so I can only put charge on the 7th and 8th and 9th floors, or the first floor, and so I can only park cars. So this is how I'm going to put donors and acceptors in there. So I start off with the forbidden band gap, and maybe I got a few parked cars on the first floor and a few up in the 7th, but how did these get here? These ionized, right? There's some thermal energy, and so these jumped. So this is intrinsic material, where the electron hole pairs are an equal quantity, because every one of these is a thermal ionization event. But if I did my doping thing, I introduced that substitutional dopant, and I chose my dopant well. What's the criteria for a good dopant for this guy? I want it to have an energy level where where its activation energy is modest, so it's fully ionized at kT. I want it to be able to go into the lattice substitutionally, right? Because if I can't put it there, then it's of no consequence. And when I put it there, the third criteria is I want it to stay there. Like lithium has actually got the electrical characteristics I need in some material systems, but lithium will move away from me. So if I run my cell phone for too long, probably the doping's going to move away and disappear, and all of a sudden my cell phone will stop working. So this is what it is at cold temperature. The phosphorus atoms has that fifth electron, but at kT starts to become finite. That extra electrons just run away. And here's similarly the acceptors. So this shows you what you want to choose. This gives you one of those three criteria for a good dopant. Here's Fermi-Dirac statistics. Don't know who that is. Fermi-Dirac statistics, fermions versus bosons. So Fermi-Dirac statistics is basically the gumball machine model, right? I have all those energy levels at the low, the first floor, second floor, third floor, fourth floor. And I start parking my cars, I start filling up the gumballs, and they fall to the bottom. And so I turn this on its side. This is energy going this way. So they're filling up. This is the bottom of the gumball machine. I fill it up, and then I get to the watermark level. I run out of gumballs, right? But at a finite temperature, those gumballs have energy. They're more like popcorn or Mexican jumping beans or something like that. And so they're jumping around, and they have some kinetic energy. And the hotter I make it, the more they jump. And so they're jumping up. And so this is an easier way to think of it in my mind. This is jumping up. Now, if I map that Fermi-Dirac smearing of the energies onto the allowed states, so this tells me how many cars I can park on the 7th floor, the 8th floor, the 9th floor, the 10th floor, the 11th floor. This shows me how much I can park on the first floor, the first sub-basement, the second sub-basement, the third sub-basement, right? And so, and then I put this on, this is the probability that those parking spaces are filled, and this tells me then how many cars I have down on the first floor and sub-basements. This tells me how many I have up on the 7th and 8th and 9th floors. And in the middle, I have my forbidden bandgap. I got a big Kentucky Fried Chicken in there or something. So then I have this, and so it's the watermark level. So as I fill it up with electrons, it moves up. And as I make it electron poor, p-type with full holes, it becomes electron poor, and it starts to fall down. Yeah, this is basically the same thing. And there you finish with that. And carrier statistics. Okay, so now I have introduced the charge. We're getting into the final, believe it or not. So once I have those carriers in the system, I have cars that can move around, and I have charge that doesn't. So remember, kT is a statistically average energy. At room temperature, this is 26 millielectron volts, which means some electrons have less than 26 millielectron volts, and others might have 40, 50, 60, maybe they got as much as 800 millielectron volts. So that's germanium. Maybe some have 1,100, which is silicon. So there's not going to be many, because that's way out there. But there might be a few, right? We got Usain Bolt. So electrons have their few outliers. Yeah, that doesn't tell us much too new. So we have the Fermi-Dirac. So electrons are fermions. In other words, they obey Pauli exclusion principle. 1 electron per state. That was the basis of the origin of the bandgap. One of the conditions. And so it depends on the density of states. You know, how many cars can I park? So this shows me where my Fermi level will be. My Fermi level is sort of, the probability of occupancy is 1/2. So it kind of tells me how filled it is. So here you can see this is weighted to the bottom. This is weighted equally, so it falls in the middle, and this is weighted towards the top because it's so shallow at the bottom. So they end up with 3 different Fermi levels calculated by that. Yeah, so here you can see the density of states showing, so this goes up parabolically. And we've seen that before, electron concentration. So now we can calculate, we can go through these very nasty integrals, but probably we are just going to calculate the free electrons and free holes really based on this. These are the ones we're going to want to use, intrinsic carrier concentration. So if we know the difference of the Fermi level from the intrinsic level, which is the EG over 2 point, I can and I know what the intrinsic carrier concentration is because I've maybe selected my semiconductor, then I can calculate the number of free electrons to free holes. And the only thing you need to commit to memory for an equation would be N naught P naught equals Ni squared, so you can just eyeball it. Order of magnitude, yes, Ben?
This is non-calculator, yes? So
Yeah, so you should be able to do in your head the idea that P times N equals Ni squared. So if I said it was silicon, it was about 10 to the 10, and I gave you N-type doping of 10 to the 18, I would hope that you could tell me how many holes I have.
100?
Yeah. That's as calculator intensive you're going to have to do. Okay, so you can, and this is relegated to homework, so you can calculate to the high precision where those energy levels are. I like these. These are much better diagrams. This is now starting to get to be realistic because it shows you how these interact, the Fermi dirac, the density of states. Those are some nice. These are from the Little Z book. Yeah, and I like this because it shows you the whole thing. It shows the crystal, kind of brings you back to the crystallography. Here's the silicon. I have no impurities, so the only electron-hole pairs are the ones that are ionizing across the gap. And so I'm breaking a bond, and those are ionizing. And so therefore I get the intrinsic carrier concentration. Or I can put in a phosphorus, creating that donor level, which ionizes, which skews this up. Yeah, these are nice diagrams because they really tie it all together. And this ties together the boron. The opposite. It's putting in the energy level there by the boron substitution. It's missing an electron, so it steals an electron from the valence band, thereby creating the free hole. And so it creates this rich area of holes. So it's p-type. Here's the whole thing together. And so we end up with that intrinsic carrier concentration, Ni. So Ni is just basically this. My undoped semiconductor, how many jump the forbidden band gap? So Ni is pretty much counting how many of those electrons are up there at any given time. So for silicon, I have 1.5 times 10 to the 10. But remember, how many silicon atoms per centimeter cubed? Per centimeter cubed. How many silicon atoms do I have? 5 times 10 to the 22 per centimeter cubed. That's how many silicon atoms I have in 1 centimeter by 1 centimeter by 1 centimeter. Right? 5 times 10 to the 22 silicon atoms. So 1 silicon atom out of every 10 to the 10, right, roughly, is ionized. Right? So it's a very, very small percentage, but it's enough that I get a fair amount of charge there. Finite amount of charge. You don't want to do this in most cases where it's N-type and P-type at the same time because they compete against each other. Yeah, this is also not so good. Yeah, so here's well, there's p-type doping, n-type doping. I'm not sure if that's really telling us anything new. This is testable. Remember, we go through these three. What I in the lecture I said, be able to draw the band diagrams associated with these three regions. What's going on? Do you remember that? Probably you don't. That's why you're here. So let's go through that. So ionization means that, let's pick on n-type. So I think this is a donor level, conduction band, valence band, high temperature, medium temperature, low temperature. So this is ionization. Extrinsic and intrinsic. So at low temperature, only a few of these have liberated. Not many, but most of these, this electron may be coming there, but these are still there. So at low temperature, these donors are neutral. Those electrons are sitting, floating around that nucleus, and so the nucleus has an equal number of protons, so it's actually electrically neutral. So they're still tethered to the phosphorus. So that's what the ionization is. This is really cold. As I start to heat up, these start to release. And when I get to extrinsic, they've all released, and I have this holding pattern where it's over a large temperature range. This is 1 over T. Those have done their donation. So they've donated. And then what happens here? I still have this. This has not gone away. But what's happened additionally? I've given it a hot foot, right? KT has now gotten, no longer is KT 26 millielectron volts. KT could be 200 millielectron volts. Now it's starting to be a large fraction of the band gap. So there's quite a number of soldiers that can make the leap. So I start to get band-to-band ionization. Right? These things are going crazy. And so much so, and every one of those leaves a hole, and every one of those creates an electron. So all of a sudden now I have 10 to the 15 intentional dopants, and I have 10 to the 16, eventually 10 to the 17 of these thermally generated. And so all of a sudden this is overwhelmed. Up here, then N might be 1.01 times 10 to the 15, times the 10 to the 17. And this is 1.00 times 10 to the 17. Okay. So I've perturbed it. It's moving to intrinsic. Of course, my intrinsic carry concentration has changed too because it's hot. Remember, that also goes up with temperature. How do they move? So then that's kind of the final installment. Once I have created these free carriers, I need to make them move around. And so as we make these devices, they're going to move by two stimuli, drift or diffusion. Drift is the electric field, diffusion is the concentration gradient. That's what makes them move. So electric field causes the electric field, they start to move with a certain mobility. And Diffusion is tethered to that through the Einstein coefficient, Einstein relation, sorry. D over mu, that's supposed to be a mu, KT over Q. My bad penmanship, sorry, I am a doctor, so I have bad penmanship. And then we get the electric field is really not, they're not going in a straight line generally. They tend to scatter, and they just happen to be herded from one side to the other by the electric field. And yeah, so we can move them around. I guess the more, oh yes, this was the lattice scattering. You probably can get some questions related on this. So we have two rate limiting steps that limit the mobility. Lattice scattering is what? It's not a good name choice, and so don't blame me. Some predecessors chose the. What is lattice scattering? What is this really from?
Vibration of the lattice and the electrons running into it.
Yes. And what is vibrational energy? Heat. Yeah. So this is heat. So this is temperature. So as I make it cold, the vibrational energy, the phonon population shrinks. I get less scattering. So as it gets colder, it can move better. Right. But then I get the impurity scattering, those little defects, those little point defects, the doping, all these things. And so this ends up being, as they move slower as they get cold, they move more slowly. And as they move more slowly, they're influenced by these perturbations in the crystal more dramatically. In fact, what you would probably see is that probably roll over like that. So as the doping goes up, the lattice scattering is pulling it down because you got more opportunities at the higher doping level. So that's probably how. It doesn't influence here because this is dominated by the heat scattering. So that tends to be how a series of experimental curves end up being. So it does this, and so the impurity scattering is modulated by its doping density. And so the mobility similarly goes down. Mobility is kind of like the speed limit. And so mobility, the ability to move through the system, so as the doping goes up, the mobility goes down. This is the Felix-Baumgartner effect, right? We accelerate through an electric field, but eventually scattering brings us to some quiescent saturation velocity. Similarly. And this is probably one of the final slides. Recognize I can measure mobility, I can measure carrier concentration by the Hall effect by simply having a bar of good semiconductor, and I can measure its properties by putting these contacts on it and putting a small voltage across it, sending some current through it, and then immersing it into to a magnetic field. And I can measure probably between these electrodes through the right-hand rule. I can measure the deflection. The electrons are going to come down by the right-hand rule. Okay, this is going this way, this is going that way, so it's like that. So then the carriers are turning and they're coming towards the one electrode, and I measure a deflection, and I can measure a few millivolts. Based upon that, trust me, I can calculate mobility, and I can calculate carrier concentration to quite high degrees. So the Hall effect is very powerful. Usually, anytime someone has an epitaxial reactor, they usually have a Hall effect test setup right next to it, nearby in the lab. Oh, sorry, I was focusing on the electronic properties. I forgot the optical. That is the more final thing. So I can optically excite, I can optically emit, right? I can make solar cells, I can make LEDs, I can make lasers. And it's simply all those energy levels that are now in play, that you now have seen expressed, are now all gained for excitation and recombination and so forth. So it's just expressing all the allowed energy levels. Do you remember what this is? This is where a high energy photon is greater than band gap, so it goes way up into the, it goes way up here, and then it's going to move down to the global minimum, right? So this is the global minimum. So it may have, so it may capture a photon that is larger than the band gap, and then there's this. What do you call this? So thermalization, it's casting off heat, it's casting off phonons. It does this thermalization where it ricochets down and loses its heat. And so I can measure, I can shine white light through, and I can see the absorption edge. So this is indicative of the band gap, because light that is of an energy below the band gap, it just penetrates through like a glass window. If my energy is higher than the band gap, it's going to be absorbed. Ben?
And I know you said this before, but that movement is quantized because of the phonons? And
Yes, there are phonons. That gets in more of the indirect band gap, where you have to make a precise, where this has to precisely come, and the vector diagram has to exactly match and so forth. There's no boundary constraints, so it's just going to cast off phonons that are represented in that material. There's no boundary conditions. It's just ricocheting down. It's more like that pinball. Right. Yeah, so here you can see the wavelengths expressed. And yeah, so if you have a trap, a defect, one of those Frankel defects, substitutional defects, vacancy defects that might create an energy level in the forbidden band gap, that can also be in play now if you have a poor quality crystal. And yeah, recombination. Yeah. Oh, this is the generation recombination that I'm talking about now in class. This is the beginning of it. And it's simply that if I excite something up, it's going to have a dwell time, and then it's going to fall back down. So I can generate, but if I generate, then they're eventually going to recombine. They balance each other. And if I have too much generation for a while, then recombination will increase to bring it back to, we'll want to bring it down to equilibrium. And yeah. And then the motion, drift versus diffusion, right? Diffusion wants to move it out, and drift wants to move it over. So then you put it together, and we get the Haynes-Shockley experiment. So if you hear me say Haynes-Shockley on the exam, that's what this is. You should say it. This guy's. Bad job on these guys. So this is the Haynes-Shockley experiment. So you basically send in this light pulse, this delta function of electron hole pairs, and it's going to send it down, and if you apply a voltage, the ensemble is going to move down by drift, and diffusion is going to cause it to broaden out, but they're really manifestations of the same thing through the Einstein relation, and so you can actually measure, it's another way to measure mobility and diffusivity. Yeah, so there's the diffusivity. You can tell by how much it broadened by a given time. You can actually calculate the diffusion coefficient. Because you can see that pulse on an oscilloscope, essentially. Yeah, see, here's your oscilloscope. You wire it up. You got a pulse generator. You're driving it. You got an oscilloscope, so you can measure that. Isn't that the end? Yeah, finally the end. Okay, sorry. A lot of material. But it's all foundational, and we can really start to build some interesting devices from here. If you have any gas left in your tank, I have a little bit. You can start to pepper me with questions. Yes?
Sometimes the terminology for like diagrams and stuff, like donor distribution profile, or there's some disconnect terminologies that are used.
What
charts do we have to know?
Yeah, so he's asking about vocabulary, getting lost in the words. I won't want you to sit on your hands in the exam. If there's something like a term and you say, unless the term is so fundamental that I can't give you the answer without answer your question without giving away the answer to the question. But if you're tripping on a terminology, maybe because the books sometimes use VBI, V0, right? It gets confusing. You just challenge me on that. Raise your hand. Don't be timid. I try not to make the exams too long because it's just these word answers, and that's why I take the quantitative part out of the exam so that we have time to have a little repartee. And if someone asks a good question, then you'll see me write I'll write a correction on the bulletin board, on the chalkboard, so that everybody can benefit. If I think it's a fundamental blunder or ambiguity that I might have accidentally created. So that's a very good question. Yes?
Could you just give us a sample question? It doesn't have to be similar to the midterm. I mean, just the format. Just give us any sample question.
What is the why does a carrier have a saturation, a velocity saturation? Explain in a sentence or two.
Could you answer that?
Well, it would be the Felix Baumgartner effect, that the carriers can experience the collisions in the lattice that will, and collisions with the phonons that will slow it down. And so there's going to be a maximum velocity through which it can transit because of the collisions. Collisions. The key word would be collisions.
What would be the best way to study for this?
I think your being here is the best way to study. I think the fact that that all of you are engaged and paying attention, and I know some people have time conflicts, so I hope you can watch this video. I hope that the recording worked. I think that's fundamental, is you hear which things have I gone over like 5 different times. There's gonna be a question there if I've emphasized it 5 different times.
Because you can't, yeah. Like just doing practice problems wouldn't really be good.
No, it's not. No, this is. You understand what makes? Yeah, it's just the fundamentals.
I have to give a suggestion. See which of these diagrams these gone over multiple times or have parallels in the book, and read how the book describes it. All right, that'll be good. That's all I can really think of.
Yeah.
Would you require us to draw anything or?
Oh, yes, that's a very good point. Very good. Thank you, Ahmed. Pictures are worth 1,000 words, and if you can illustrate your answer pictorially, that's great. However, just be careful. Don't think a picture is self-evident. If there's a question and you just draw a picture and then move to the next question, I wonder, where did this picture come from? It came from thin air. Did you just copy that off the guy next to you? I don't know where this picture came from. If you can draw the picture and explain what you mean, you can reduce the number of words you have to use because you got a nice picture explaining. Then, if you do, I got this, and therefore this is the thermalization happening, then that's really a nice, crisp answer. It's not mandatory you draw a picture, but in some cases you may find a picture is beneficial to explain. But just be careful that a picture is not self-evident. I'm not a mind reader when I grade these, so don't think that just because you slap down the appropriate, you just memorize that. That picture, Berger always draws that picture every time he talks about this concept, right? You're probably going to get 0 points for that, to be quite honest, until I see that you've thought about it.
So write a sentence that says why the picture answers the question.
Yes. Tie it together, so it's not something that just comes out of clear blue. Yeah. Yes?
How many questions do we have?
I don't know.
Are you writing it so that will be done, it will take the whole 55, or just take the
55, 60 or so. I don't like the exam to be a timed event. The first midterm, the second midterm, were it's a little bit hard sometimes. Some people are faster, some people are slower. You may find that some people finish in 40 minutes and walk out and actually have done a very good job. So don't be distressed by that. Some people can just rattle it off. Others might need the full 60 minutes. I will borrow as much time from that 10 minutes in between as I can until the next class is beating down the door. So the first midterm is kind of on the hairy limit. The second midterm we're still, and then the thing I always do is the final exam is actually the same length, pretty much, as the midterms. However, we got twice the amount of time. So if you were a little bit penned in, if you're not one of these people that answers questions quickly, then the final exam is the opportunity to redeem yourself, because that should not. The last thing I want on a final exam is for a whole bunch of people to still be sitting there when the time expires. I want everybody to be gone before the time expires on a final exam. So that's your chance to redeem yourself. Now, one other thing that comes to mind, I want to make sure a message gets across. Do not have diarrhea of the pencil. Some people will sit there and they will want to answer and write down every thought, and they're writing an encyclopedia. You don't need to write an encyclopedia to get full points. Some people can crystallize their English and write some really succinct sentences, 1, 2, or 3 sentences or so forth, maybe. Some might be 4 or 5. And if you get your idea across very crisply, you don't need a lot of words. And so you should not have to get writer's cramp to get full points. I've had some people give some very Spartan answers, some very just spot on, very direct. They really knew what they were talking about. And there was just short staccato answers, full sentences though. And they were still able to capture full points. And so filling the page up with graphite and turning it brown, like diarrhea of the pencil, is not necessarily guaranteeing you full points. In fact, sometimes students that do that are trying to hide because they don't know what the answer is. So they're just saying everything that comes into mind. And I see that, and I know that. I know that you're just kind of trying to get some partial credit. Well, I don't give partial credit. When I see your statement B conflicts with statement A, then statement A, even if it's right, is now invalidated. 0 points, because B just showed me that you don't know what you're talking about. So don't think more is better. Okay. What happens historically is students are rattled on the first exam, first midterm. Scores are low. The second midterm, much better, and the final exam, really on mark. And so I'm pushing you and hurting you, and you will get there, because year in and year out I have. And before you start to get severe anxiety, I grade. You'll never be able to pin me down on what your letter grade is partway through the semester. I never want to, because I look at the vectors. If you have an exam where you're a 32, and then you do a 75, and then the final exam is a 93, well, there's a large level of forgiveness if you did that trajectory. And I remember, because this has accumulation, not only is the device concepts cumulative and so forth, so I have a strong level of forgiveness of this. So just to recognize, I will force you, or else, to get this way. And so I give you the benefit of the doubt. The other happens that some people will start off here, and they'll get complacent, and then they phone in the final exam, and then I start to wonder, that 97 and 100, what happened there? They got senioritis or something. And so then I can hit that guy hard. So don't feel that the world is lost if you start off with a 32. It happens.
And the other point being the final will always matter.
Yes. I give a level of forgiveness. Yeah. In fact, I look at that and I can actually swing you a whole letter grade. That's my range. I can swing you that if you finish with this profound A level quality work and you had some C work before, then I might really so I have a strong level of forgiveness. So you can really benefit. Not too many people follow that trend. So, okay. Hopefully this recording worked. Let me see.